Most attempts to explain the theory of relativity to an unprepared listener end in total failure. But we'll give it a try, so if you still want to try and understand it, watch and listen very carefully. I'm currently moving in a straight line at a speed of 20 inches per second, and right above my head, a portrait of Albert Einstein is moving in the same direction and at the same speed. The distance between us is 6.5 feet. At some point, I will send a signal to the portrait, a beam of light. Its speed is of course equal to the speed of light, which is 186,000 miles per second. Obviously, the beam will reach the target almost instantly, moving along a trajectory which is practically perpendicular to the ground. Now, let's change the conditions. Einstein's main assumption, which he actually based his theory on, is the constancy of the speed of light. In other words, 186,282 miles per second is the maximum speed anything can move at in our universe. Nothing can move faster. That figure is, of course, very considerable. So for a scientific experiment, let's slow it down a little. For example, let's make it 3 feet per second. So now the light moves like this. It looks almost like a scene from a sci-fi film. So this is a new maximum. Now in this incredibly slow world, I'm moving at the same speed along the same trajectory. I have a portrait of Einstein flying over my head at the same speed. And I'm sending it a light signal again, but this time its speed is not 186,000 miles per second, but it is 3 feet per second, as we agreed. How do we determine how much time it will take the signal to reach Einstein's portrait from where I am now? Well, it's a simple formula. Time is distance divided by speed. The distance between us is 6.5 feet. The speed is 3 feet per second, meaning it will take roughly 2.2 seconds. That seems to be correct, but only from my position. If you look at the situation from the outside, everything will be a little different. The third-party observer, in this case our cameraman, will see a completely different picture. From his perspective, the beam will not move directly perpendicular to the ground, but diagonally, because the portrait of Einstein and I are moving almost as fast as the light itself, which means that the beam will travel a greater distance. If desired, this distance can be easily calculated using the Pythagorean theorem. The paths of motion form a triangle, and the square of the hypotenuse is always equal to the sum of the squares of the other two sides. So in this case, the beam has overcome the distance of 7.2 feet. Now let's go back to our formula. As we said, the speed of light is constant. In our case, it is 3 feet per second. And if the distance has changed, now the distance is 7.2 feet. And if the distance has changed and the speed has remained the same, then the time must have changed. So the time will be equal to 2.4 seconds for the cameraman, which is a little more than for me here. So for Einstein and me, time seemed to slow down a little in those 2 seconds. For the cameraman, it was a quarter of a second longer.
Let's look at it again. This effect of relativistic time dilation can be observed only at ultra-high speeds close to the speed of light. However, as it turns out, time depends not only on speed but also on the strength of gravity. This effect was also described by Einstein. Its essence is as follows. The closer you are to any massive object, a planet, a star, the slower the time flows. The first time Einstein's theoretical assumption was practically proven was after his death. In October 1971, Joseph Hafele and Richard Keating flew around the world twice with sets of Cassium atomic clocks and then compared them to the same clock that all the time had been quietly ticking on the territory of the U.S. Naval Observatory. The clocks that were in space had really slowed down and lagged behind by 50 billionths of a second. A little number for a simple human, but an incredibly large one for humanity. Today, the same effect is felt by astronauts on the ISS. First of all, they move at a speed of 17,000 miles per hour, and secondly, at an altitude of 250 miles above the sea surface. This is the altitude of the station's orbit. The gravity there is 11% weaker, but flying on the ISS isn't the secret to extending your lifespan over others. To gain 1 second, you would have to spend about a century on the station.